Hello everyone, this is Dr. Mia again, ECE100, class number 3. We're going to do equipment basics in this class too, so let's get started here. So we did some circuit symbols in last class, so let's see, can you remember those or not? So we're gonna test them in the class, how much you remembered from the last class, and also talk about this circuit in the class too. So wire is a very important element for any circuit or electrical systems. Wire basically connect two points together in circuit or in the electrical systems. So what do you have to consider before you select a wire? Remember that wire carries currents. So that means you need to know how much current the wire can carry. So you need to know the current rating of the wire, right? Then also wire has insulations. That insulations depends on sometimes how much voltage it can carry. So because electrical breakdown could happen, so we need to know the voltage ratings, right? Then also, where are you using the wire? So that means environment. Is it indoor, outdoor? Is it underground? Is it a conduit or free space? And so on. So that also need to be known before you select a wire. Then also, what kind of wire are you using? You're using solid or stranded. So these are the things you have to consider before you select your wire for your applications. So solid versus stranded. You can see from here that we have two pictures, one stranded, one is solid. So what are the advantages and disadvantages of solid and stranded? So solid usually less expensive, and also is easier to make non-solder connection. Right? And it's also solid is if you less reliable connection, because if you break is break, there's no other strand to hold on to. So also less reliable connection. And also if it's like a little bit thicker wire, not easy to bend. So these are the thing of the solid wire. Standard wire is more reliable because of more strand. And more flexible. It's also more expensive. So these are the thing between solid and stranded wires you need to think about for your applications. So in your industry application, there's some color-coded wire out there that we use, like red, yellow, orange. Those are basically for positive voltages, and black is normally for negative or ground or reference voltages, and green represent the main signal path. This is all true for DC connection. For AC is different. I'm not gonna discuss it over here. For AC, you have different color code and different electrical code for AC. So I'm not gonna get there. But for DC, this is the word: radial orange or positive voltage, black is negative or ground, and green is often a single path for DC connections. So how much current can go through a wire depends on the resistance of the wire. So resistance R is directly proportional to L over A. And if I complete this equation over here is rho L over A. So rho is the resistivity of the wire or of the materials. L is the length, A is the cross section area. So you can see that if you go a longer distance, you have more resistance. If you have a let's say thicker wire, which is the greater cross section, you have less resistance. So in America, we use AWG, which is American Wire Gauge System for the wire. You have a handout for that. Every wire gauge has their cross-section area, diameters, and also the current rating. And also is that there's two current ratings, worst case and the best case. Worst case means if you're using the wire in a very confined space like conduit, if we use there less space for heat dissipation, as well as also each wire generating their own heat, so it'll be more heated. So in that cases, you have to use the worst case scenario. If you're using the wire by itself in open space, you can use the best case scenario for your current. For our application in the breadboard, we always assume that our wire has zero resistance. So we don't consider any resistance for our connection in the breadboard. We're gonna solve this problem in the class. So now let's see what can cause errors in your measurement. We talked about that. So error can come from different places, different factors. Like your source of error can come from the air moistures, room temperatures, instrument resolutions, and can come from test equipment drifting. The drift means just is get older, is basically try to deviate from their actual calibration. So it's good to calibrate equipment every year or often to make sure that they're not drifting from their true value, and so on. So these are the things. So test equipment, you're testing with something that drifting with aging could have affect your results. Resolution, you're measuring the data from using an instrument. That instrument resolution could give you some error there. Let's say if you do 3-digit over 6-digit resolution. So obviously your 6-digit will give you better result than 3-digit. Like if you have anything in micro, you cannot read with 3 digits. You can only read milli in 3-digit. For micro, you need 6 digits. So if you're measuring, like say 20 microamps, you cannot measure with 3 digits. That means that is equivalent to 0 for that equipment. And also temperature could change your result, because if something done in a lab setting where the temperature is a lab temperature, if you're trying to reproduce the results in your lab, your temperature is different, then you get different results. And air moistures sometimes give a different result, because if your device or your equipment sensitive to the moisture in the air, that could be different results too. So um, which one is the most significant in your results? That could be that instrument resolutions and the test equipment drift. So these two are the most significant: instrument resolutions and equipment drift. These are the most significant error in your measurements. Never ever say that is human error. If you have a human error, go back and correct it. Human error is not accepted in any measurement. So for the DC power supplies, we get two things from the power supplies. One is the voltage and the current. So one is called constant voltage. That means that equipment should give you the constant voltage or fixed voltage as you want. So that is basically you are getting a constant voltage from that equipment at the terminal. That's the constant voltage. And constant current, that means your equipment should give you a constant current um, as you wish. So these are two settings. You can do both of them in your device, like Agilent power supply we have in the lab. Uh, but in the lab, what we do, we basically use regulated power supply. That means you regulate your output voltage, you regulate your output current. So in the lab, we use regulated power supply. Power supply. That means we regulate how much we want from the supply in terms of voltage or current. This is the Agilent power supply here, so you can see that the voltage has 2-digit resolution. That means we can only measure to 100th of voltage, like or maybe you can measure 0.01 volts. That's the lowest we can measure here, not lower than that. For the current, we have 3-digit resolution, so we can measure up to 1 milliamp, not smaller than that. So constant current, constant voltage. If you can see that this right now is showing CB, that means it's operating in constant current. When this sign will change to CA, that means it's is operating in constant current mode. So there's a two different settings for the constant current and constant voltage. So how do you know that you are having a current limit or voltage limit? Let's start with the Ohm's law. Ohm's law says that V equal to IR, right? So for a device, normally, if I connect over here, let's say we're connecting 12 volts to and set to 3 amps. So your if you're doing that, your R is should be 12 volts over 3 amps, give you 4 ohms, right? So if you're supplying a 4 ohms load with a power with a 12 volt supply, that is your 4 ohms, you're getting 3 amps. So that is fine. See, if you now your voltage set to 12 volts is constant voltage, right? Then you are connected to 4 ohms, you're getting 3 amps. Now, if you change the load to, let's say, 2 ohms here, not change the voltage, you change the load to 2 ohms now. If you do the 2 ohms here, your Ohm's law will say that your voltage, all right? So your current would be, let's say, 2 ohms, right? You have 12 volts, and your I will be 6 amp, right? Your I will be 6 amp. So if you constant voltage supply out there, if you don't have any limit on current, so that will supply 6 amps. But if you limit your current to 3 amps, now if you limit current to 3 amps, then what will happen? So to obey the Ohm's law, now you have 2 ohms and 3 amps, so your voltage should be 3 amps times 2 ohms would be 6 volts. What will happen now? You cannot get more than 3 amps because you limit the current to 3 amps through the resilient power supply, and your voltage is also limited at 12 volts. Voltage cannot go over. What will happen? To adjust the Ohm's law, your voltage will come down to 6 volts. So that means to obey the Ohm's law, your voltage now, your supply will be 6 volts. That will satisfy the Ohm's law. What I'm saying over here, so your voltage and current supply, when it says limit, that you cannot cross the limit. So you have to obey the limit. If you set 3 amps limit and 12 volts limit for the power supply, and if you add a 2 ohms load now, right? So you cannot go, your set is 12 volts, 3 amps, you cannot cross any of them. So with the 12 volts, you right away hit the limit of 3 amps, so you can stay there. So that means your current is 3 amps, your load is 2 ohms, then you have a 6 volts. So now your supply over here will go down to 6 ohms. So now your supply over here would be 3 amps, 6 volts with the 2 ohms. Right? Do you understand that? So you cannot cross the limit. You have to in the limit. So if you hit you have the current limit, you cannot increase the current. So your voltage needs to go down to obey the Ohm's law. That's all for today. I'll see you guys for the next class.